Alright, so these notes are the second part of force, where we actually talk about Newton's laws. If you remember when we were going through the first set of force notes, I mentioned that really this unit could be taught either way, which one going first, the Newton's laws or just basic forces. And I just personally feel that going over what a force is and what those diagrams look like make Newton's laws make a little bit more sense, but really it's kind of a toss-up. Alright, so here we go. Alright, so most of you remember from elementary and middle school that Newton had 3 laws. So the first law is the law of motion, which we can talk about inertia with that. And what this states is that in the absence of a force, an object that is in motion or an object that is at rest is going to stay doing whatever that was in motion or at rest until some sort of outside force acts upon it. So, for example, if I had, of course, all this stuff is not raining. If I had a ball, and just like in that little force lab that you saw, the ball is sitting there, the ball is going to stay in one place, okay? But if I add an outside force and push it, it's going to roll, okay? So it stays at rest. Well, not really, because this obviously isn't level, but there you go. Stays at rest because it is at rest, and then it would stay in motion until some sort of force acted upon it. Okay. So, in other words, it's going to keep doing what it's supposed to do until some sort of force makes it change its motion. So if there was a bullet that was fired, it would keep going until it hit whatever barrier, so a brick wall, whatever that might be. A ball that is thrown up in the air until it's caught, okay, would keep on going. Of course, we know that there are other forces, like we talked about, friction, those kinds of things, gravity, that are actually going to prevent this from happening forever. But ideally, in motion stays in motion, at rest stays at rest. All right, so, once again, we're looking at some force diagrams like we saw before. So if an object is at rest, okay, it's going to stay at rest. And then if I have a force that pushes it towards the right, it's going to move to the right. Same thing if I have it going a force to the left, it'll move to the left, okay? If they're going in equal amounts but in opposite directions, one's going to the right, one's going to the left, the object, of course, then would not move, okay? Now, if you have an object that was in motion, so like this ball, okay, and if it was moving and I push it, it's going to move faster, okay? So if it's moving along to the right just because it's rolling and then I push it, it moves to the right and move faster. But if I have an object and it's moving to the right and I touch it, okay, I'm going to slow it down. And of course, this ball is so lightweight that doesn't matter much. But think about like if someone was rolling down a hill and you're just kind of there like putting an opposing force to kind of stop it, you would slow it down, but maybe not pull it to a complete stop, okay? And then, of course, if they're equal but opposites, okay, one pushing towards and one pushing away, it's going to move along at a constant speed because that equal and opposite force that's opposing would cancel out, so whatever speed it was going, it would continue. All right, so the first law, once again, is resisting change in motion, okay, and the more mass it has, it would need a larger force to change that motion. So if we think about this, the basketball player and the ballerina, the basketball player would probably have more mass than this ballerina, so therefore he would take more force to move. All right, so then we talk about momentum, okay? Momentum is related to how much force it's needed to change the object that's in motion, and that's going to depend on direction. So here we have a new equation. Momentum equals mass times velocity. So P is what momentum is for, and of course M is mass and V is velocity. And you know that whenever we have an equation, what I like to do is I like to draw a triangle. So since there's no fraction, I can go ahead and put the P up top, okay? I can put the M and the V on the bottom. All right, so momentum is mass times velocity. All right, now what we like to do in class is we've always liked to put in the units, so I'm going to go ahead and do that now. We know that mass is going to be a kilogram, and velocity was a meter per second, okay? So then momentum is going to be a kilogram times meter per second, and that's what I have right here, okay? So whereas with newtons, we could make the newton a kilogram meter per second squared, we can only make this just a kilogram times meter per second squared, okay? So that's that unit. All right. Oh, my pages are getting a little together. All right, now, so once again, momentum is mass times velocity. Force, okay, so we talked about what a force was, and I kind of gave you a little bit of a preview in this when we were talking about basic force in the last note set. But you have the change in momentum over time. So you're going to have mass times the change in velocity, and if you remember, the change in velocity was acceleration. So you have mass times acceleration. So force is going to be equal to mass times acceleration. So if I wanted to make a new triangle, which of course you know I do, force is going to go on top, mass and acceleration. Okay, so this is that unit that we had in the last note set. Force was in newtons, mass of course is in kilograms, and acceleration, you remember from our last unit, was a meter per second squared. Okay, so really force, okay, is a kilogram meter per second squared, but we talked about how we can make a nice, clear, concise unit of it just being a newton. But if you needed to know what that really was, that is what a newton is, kilogram meter per second squared. All right, so now we move on to the second law. This is about the change in motion of an object, the acceleration, being directly proportional to the forces that are unbalanced, that are inversely proportional to the mass. Okay, so basically now we're talking about how much force it takes based on how fast it's going and how much mass is there. All right, so in other words, how much force is necessary to make it move. Okay, so here's where we really play in this equation, mass times acceleration. All right, so when we start thinking about this, okay, oh, let me go back a step. I thought I had more examples there. Think about a wagon. Okay, I've done a lot of moving children in wagons the past couple of days. So if I had one child in my wagon, I could run all over the yard, especially if it's my 1-year-old, and we could just go, 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 because I got like a 20-pound kid in a wagon, and we're just rolling. Well, then, if my middle child says, oh, that looks fun, I want to jump in, and she's like 45 pounds, and she gets in the wagon, and so now I've got about 65 pounds that I'm pulling in the wagon. I can still do it. We might not go as fast, okay? But then if my third kid says, hey, I want to get in too, so then I have a 9-year-old, maybe weighs around, 55, 60 pounds. We'll go with 60 because it's easier to do the math. I have that 6-year-old who's like 45-ish pounds, okay? And then I've got my, we'll just say 20-pound 1-year-old, okay? So I've got 60 plus 45, that's 105, plus 20 more, okay? That's 125 pounds. That's a whole lot harder to move, okay? So it's going to take a whole lot more force for me to be able to run around doing that. So here we have our little force diagrams once again. And what this is going is how this mass and acceleration works. So if I have a 3-kilogram box, okay, and it's moving along with an acceleration of 4 meters per second, which remember is meters per second squared, I'm going to say 3 times 4, so the force would need to be 12 newtons, okay? And so once again, there's that reminder of meters per second squared or meters per second. All right, now something that we have to remember is weight and mass, okay? They're not the same thing. Mass is how much matter is in the object, whereas weight is gravity playing a part on that. So for this little example, this little person here, their weight on Earth is around 560 newtons because that would be their mass times gravity, which is 9.8. But on the moon, okay, there would only be a weight of 90 newtons because gravity on the moon is much less. But notice that the mass is always 56 kilograms. So mass stays the same, but weight can change depending on the acceleration, that gravity. All right, so that's what I was saying here. Weight and mass are not the same. Mass is how much matter is in it, whereas weight's dealing with the force of gravity acting upon it. And so here is another equation to look at. Remember I told you we were going to get that equation sheet all loaded up for you. So if I wanted to do this equation, force would go on top, mass and gravity on the bottom. Once again, if I want to do my units, pick a different color here. That might be too light. Let me go with this purple. That might be too close to the blue, but we'll see. Force is in newtons, okay? Mass was kilograms, and since gravity is an acceleration, it's a meter per second squared, okay? And once again, that unit for gravity is 9.8 meters per second. That's here on Earth, okay? That's always what gravity will be, and that's one of those things on that reference guide. All right, so when we start talking about Newton's law, if they don't give you a force, okay, you might think about that you're just dealing with mass times gravity, okay, and that will be the force that you're talking about that's pulling on it, especially if they actually use it as what is its weight, okay, you're looking at the mass times gravity. We already talked about it's 9.8, and so here's an example. It says Jesse has a mass of 200 kilograms. What is his weight on Earth? So I say 200 kilograms times 9.8 because the weight, this is weight, is going to be mass times gravity. So I put those together and I would get 1,960 newtons. Okay? We'll do some more practice problems like that. And then the last thing we have here is the third law of motion. So the first law was inertia. Okay? At rest stays at rest. In motion stays in motion. The second law was dealing with mass and how much force it's going to take to move certain masses at accelerations. And our third law says for every action force there's an equal but opposite reaction. So for this, think about if you've ever been in a boat. If you want to move forward, you actually row backwards, okay? And as you row backwards, the boat goes forward, okay? Same thing with like a rocket, okay? When the rocket goes up, you have all this thrust that pushes back, okay? So the rocket is going upward, and that big old cloud of gases being exposed is going down, okay? So equal but opposite. All right, so here's an example that maybe you're more familiar with. A baseball bat is going to exert a force on the ball, therefore the ball exerts the same force back on the bat. So most of you at some point have swung a bat and hit a ball, okay, if it was just a PE class or in the yard or something. So when you do that, the ball comes at the bat, and when you make contact and swing, when the ball hits the bat, the ball is going to act upon the bat like the bat is acting on it, and so you get this equal but opposite force, okay, and that's where you feel that vibration and that sting that happens in the handle of the bat. All right, so last thing here, it says that if you are thinking about, remember how like when we had those force diagrams, we talked about how like the ball didn't move because you had gravity and you had norm pushing up on it? Same thing going on like if I were to push against a wall. If I push at the wall with 100 newtons of force, I'm not going to fall down. The wall's not going to fall down because the wall's going to push back at 100 newtons, and so we stay in place, okay? So that's why all of these things that were not in motion, something was pulling down with maybe 12 newtons of force and being pushed up with 12 newtons of force. And so that's why we called it balance, and there was no motion, okay? All right, so you'll be using these to kind of categorize. There's some more little lab examples to look at. And as always, if you have any questions, please feel free to ask.